PCA in MLF, and let me check once. So PCA, we'll see. PCA is not so tough even. Here is a very brief, but yeah, almost PCA have done here. So PCA is an algorithm where we will usually, the case is that we usually have some data, okay, and so the case is that sometimes we usually have more features. So we want to, so features means we have more dimension. So we want to reduce the dimension of the data, want to reduce the features. So that is how much dependency in each others, that usually the EDA, exploratory data analysis, will tell you which feature is more important, not more important, means dependency it will show, it will when you do the EDA. But how you will reduce the dimension of the data, and this PCA is mostly for unsupervised learning. Okay? This is for unsupervised learning the cases. So in that case, how will reduce? So this is an algorithm to reduce the dimension of the data. Okay, so we'll see in a few minutes with some examples. So this week is this session is for open and solve with us both, because the next Saturday we'll try to cover week 8 both, and the next week the 2 session would be for revision session. Yes, this is how we'll try to cover. So the PC algorithm is not only to reduce the reconstruction error, it actually so increase the variance also, to maximize the variance. So what is the variance here? Many people generally have doubt what is the meaning of variance in this PCA. Where is the variance happening? So let me present my screen, then we'll see easily what is happening here in the PCA. Okay, very short we will see it, because the in the lecture mostly proofs are there. Okay, our algorithm professor is how we will reaches to the how the PCA is actually minimizing the reconstruction error. The all things is actually discussed in the algorithm. So we'll not go to the full detail. You, if you want to go to, just see the lecture. You can easily get it. It's just not tough. Okay. What needed to understand what's happening? So I will tell you what's happening there. Okay, and we'll proceed. So just a second. So this session is open and solve with us both. We first try to cover the contents and then we'll move to the solve some problems. Okay. Am I audible clearly? Clearly, am I audible?
Yes, sir, you are audible.
Okay. So let me send my screen. So what is generally happen in PC, So PCA. So we know there are, data is, features. We know features. What are the features? Meaning many times, mostly I have taken this session. So we have discussed a lot about the features. So these are supposed the features. Okay. So we can say these are the how many features should be. We will say that many dimension of the data. Okay. Okay, this is how the meaning is. So data could be much larger, or maybe we'll here to understand the algorithm. We'll think at most 2 or 3 dimensions. So not even 2 3 dimension, not dimension. I mean to say the coordinates means large means you know it have more coordinates. Okay, that's meaning here. How maybe feature would be also more, not only the dimension. So here is in PC in higher dimension also. So mean to say it have more features in comparison of data means whatever the number of coordinates are there. Okay, so we'll see that also. Okay, a PC in higher dimension will also see. So suppose this is the data we have. Okay, so we want to reduce the dimension. Why we want to reduce the dimension? We will check using the EDA. We will see what is the EDA. We will see in the MLP mostly, because MLP is the theory part only. So you will do the EDA means exploratory data science, and you will see the dependency between the features, means how much these two are correlated. Okay. So you'll see the dependency between the features, and then you want to reduce the dimension here. Means okay, I got this, I want to remove this. This is not so important, or maybe sometimes the all features are important, but still I want to reduce the dimension without losing the information of the data. Most important, informations, okay, which is related to the data. We want to not uh, lose this information, and still we want to reduce the dimension. We want to reduce the number of features. So how we can do this? So this PC algorithm tells you how we can do easily. Okay. So one thing is that, and the second thing is many people have doubt what is the meaning of variance. Okay, why we want to maximize the variance. Okay, so it's actually depend on the PC algorithm why you want to maximize the variance, why it is so. So the thing is that the PCA, what does PCA here? PCA, so suppose I'm two-dimensional, I have some
What is the
data.
meaning of
No,
PCA?
sorry,
What is PCA?
PCA is an algorithm. That's all. Principal component analysis. Okay. So PCA is, we just give it PCA means here. Let me write principal. Okay. So yeah, the best thing is that before to start, you can ask question to me that what kind of doubt you have. Okay. Component analysis. Okay. So these three terms using makes the PCA word, and this is just algorithm. Okay. This is just a algorithm to reach or to minimize the dimension of the data. Okay. So anyone have any other doubt, any kind of doubt why this is, or what kind of doubt it's coming, or it would be silly or anything, you can just ask me. I will tell the answer. That would be good even. Yeah, like what is the PCA, somebody asked. I just told you this is a principal component analysis. What is the meaning is that I want to reduce the data some important means on the principal component. These are the features I want to reduce the dimension, means I want to reduce the features to main important feature. Okay. That is the principal component. On the principal component, already what is the meaning of it. Means important or principles. component. I want to reduce these data means dimension to the important dimension or lesser dimension, means which is more important, which is the
Sir, which
principle.
components are involved here? Which components are we analyzing?
So which so there is not analyzing. We are not analyzing. We want to find that component. In this PCA, we will find that component which is important. That is what here we are doing. We are not analyzing the component. We will actually try to find that component, and PCA does that. Clear?
Yes, sir.
Any other doubt? Any kind of doubt still? Okay. So what is here? Suppose these many datas, okay? So many datas we have. So PCS actually, if you see that, you know already the MSE, mean square error, okay? You know already it. Very similar kind of works we'll do here, but very differently, okay? The case is that suppose we have the data in 2-dimensional. So these are the suppose data we have. We want to visualize it, okay? So I want to find a direction, okay? I want to find a direction. This is your principal component, okay? This is your principal component. I want to find this component, means this direction, okay? I want to find this so that what, when we project all data on here, okay, when we project the data on here, okay, here is also the projection word is projection is involved, as in MSc also you used to see. So we will project it, okay? We will project so that, see, suppose here is your data. Once you project it, so this is your new data, right? Suppose this is your xi, so or let's say x1, okay, for the timing, let's say this is your x1. So what you projected here, so this is your, let's say, x tilde, okay, this is your x tilde I, or let's say this is 1 here, no? So after projected, this is x1 tilde, okay? Suppose here is my x2, I projected here, I projected it to here, so here is x2. So this is what your after projection, okay, I have projected. So this is your suppose x2 tilde, okay? Similarly, this is what happening. The original data is here, but the projected data is here, okay? The projected data is here. That is what we are in the, if you see in the lecture, that is what it is tilde. If you see, the professor is telling that the projected data is your tilde one, means xi tilde, okay? So okay, so this is what we are doing. So we are projecting it, but we will project with the differently also. This is not exactly we are projecting, okay? It has some formula, okay? According to that we'll do the projection, because here we'll do the reconstruction would be minimized, means once we do this projection, it will be first things the minimize, it will be minimized, means the new data you got, right? x1 tilde, x2 tilde, x3 tilde, and if you subtract from the original to the updated one, okay, if you subtract the data, this is the original one and this is the updated one, it will be the lesser one, okay? If you subtract it, this difference is very less, it is not going to be much, means we are try to minimize the reconstruction. So this is your reconstructed data. This I am telling as naming is also reconstructed, okay? This is your reconstructed data, x tilde.
Sir,
Where
I just
yes.
have a small. Yeah. Sir,
Hmm.
in this case, since you are telling, sir, this projected data, but sir,
Mhm.
is the sir projected data is not the reconstructed data, right, sir? It is because from the projection data, like if we add the mean back, like whatever was explained,
Mhm.
then we get the again reconstructed data, right?
Then you will get the reconstructed data, yes.
So basically, x1 tilde, since you have projected it becomes a projected vector basically,
So
and
that is what I'm saying. This is not exactly your projection, which is taught you learn in the linear algebra. This is a different projection. So if you see the formula of the
right.
xi tilde, that is a different. That projection is on, you know, if you see the formula, this is eigenvalue, right? Sorry, eigenvector. This is a eigenvector which have the maximum eigenvalue. According to that, we'll project with additionally will project to the mean also. So see, this projection is different. This is to visualize it. This is what is happening. I am just naming it projection. So that's why in the starting I said this projection is different as you learn in the linear algebra. Okay.
Okay, so basically this xi tilde, which we are telling it to be the projected vector, it basically is itself is the reconstructed vector also, right?
Reconstructed vector, the new vector, reconstructed vector. Okay. You will see this in MLT. You will see again this PC. Okay, if you're not able to understand, I will try to convince you how much I possibility. I will try to tell you that what is happening. But if you not understand, try to understand at least mathematically, so that once you do in the MLT again, in MLT you will see in more detail even this, and you will see what is happening on. This is what in the MLT it is told that this is what it's happening.
Because sir, actually in the practice assignments and all, so like I was going through, so like, there were some ambiguities, so that's why I thought of
Okay.
asking this. Yes, even in some of the options and all, like because since you told that this is not exactly that kind of projection, it is a different thing. It is a reconstructed vector. So thing is that because basic projected vector, the formula is different. Here we are adding the mean.
Different.
Yeah.
Yes.
So in those, like when I went through those questions, so in those questions, like I found basically this I found there was some ambiguity. So I'll let you know, sir, in which question I faced.
Which
Okay.
question?
Yes.
It is in the one the not the non-graded assignment, basically the week 7.
And
It is
practice assignment.
practice assignment, yes, because they have when I tried finding out the answer, so basically they had done only the projection part. They didn't add the mean part, basically.
Actually, there is maybe the reason if your data is centered. If your data is centered, this mean part will be off. Okay, it will be 0. I will show you with the example. Okay, I will show you with example. I have solved with assessment.
In that case, sir, the mean part was not 0 actually. So that is the.
Oh, in that case, it is not becoming 0, but it's still okay.
And I
Okay.
also saw in some discourse thread, someone was telling the options were wrong or something like that.
Okay.
Because we in GA also, I think we have some kind of these questions. So that's why the ambiguity is there.
Right.
Fine, sir, no problem. Please carry on.
Okay, so let's proceed. So this is what the different projection is happening. So this is the related to the. So this is your means in which direction. So this is 2-dimensional, and this line is 1-dimensional. It still tells you. So this is look like okay, we are doing the same projection kind of, but it is a different projection. And when we want to suppose in this is a 2-dimensional data. Okay, maybe you have the higher, maybe more dimension. Okay, and you want to project in not only 1-dimensional. Sorry. In not only 1-dimension, it would be maybe in the different dimension. So means one more dimension we want, maybe in the plane case, or I don't know. So in that case, the second principal component analysis is going to be the second principal component is this one, the second it would be tell that in which means in 1-dimensional projection you want to do, or 2-dimensional projection is it's actually told in the lecture. So in the if it is 2-dimensional, then we'll add the second highest eigenvector, and according to that the formula will be updated. I will show you the even the formula also. Okay, so means slowly how many dimension we want, according to that we'll increase the we'll add the eigenvectors. Okay, and rest all with added with the mean. Means okay, let me tell you let me show you the formula first. What is that? here. So this is what the formula. This is what the total algorithm. So what is that? See, these are the data. Okay, these are the data you have. Okay, and how we'll get that? Which in which direction means what is the how many dimension you want to project? So it's actually we want to project in one dimensional, two dimensional. It will told in the lecture. So according to that, will increase. Like see, if it is state one dimensional, then your m value is 1. If it is two dimensional, then m value is 2, 3, 4, as it told. According to that, will project that means that many m means according to that will increase the eigenvector and write the full formula. Okay, this is the summarized formula,
What
and
is
this is
X?
the second part where we'll project on the mean. This is the on the mean part.
Sir, what is
This is the
X?
separate. This is the on the eigenvector part. Yes.
I had centralized also, no?
Yes.
Step 2, where is centralization?
That I will tell you. Means here is what is happening. What is the eigenvector here we are finding? I will tell you this too. I will tell you this too.
Yeah,
Let me
but
finish it.
in the step 2, there is no centralization. No? We have to subtract this mean vector with
Yes.
all data points.
Yeah, this is the general case. If even your data is centralized, it doesn't matter. You have to step follow. If it is centralized, then your mean part would be 0 anyhow. And there reconstruction error is going to be, there is no risk reconstruction error. You will get the same data. You will get the same data.
In the second step itself, we are centralizing it, na? Xi minus x bar. That is the centralizing part.
This is the this is the part of centralizing.
Yes.
This is
So
the way to centralize.
sorry.
At C is equal to, that is helping us centralizing.
Yeah, we are centralizing the data. Yeah.
What exactly that means?
Exactly, the mean is you know, right, as from the mean how much you used to do, like from the mean, like in stat, you know, right, from whatever the data is given from, we used to subtract mean to, you know, get the variance, like that. That is what it is actually. It's happening. So exactly the meaning is in pictorial format or any other is how will tell you it.
Centralizing means
Yeah.
like things
Anyone can
getting.
tell, even in yeah, anyone can answer it.
Sir,
What is
I'm
here?
just, yeah, just
Yes.
this is my understanding. Is it like if this data is going through some transformation, we are extending or making it shorter, some kind of transformation stress situation, some vectors, some values will not change their direction. I mean, basically, these eigen vectors. So that is what, and based on that, we are driving that these are the critical values, and we should not compromise on these values. Is it something like that?
Not that much.
So
Is
centralized.
PCA, we are just conducting PCA. These 4 steps are mandatory to do.
Yeah, mandatory. Yes, yes. And generally we say it, this is we are centralizing.
Centralizing is basically, taking the subspace to the origin, basically. So, and the moment you centralize it, basically at that point of time, since we are changing the data, so what happens at that point of time, we are changing the data in such a way so that the error is also minimized and the variance is also maximized. So that is one of the main like fundamental of fundamental steps of this thing
Yes,
of
doing
PCA.
this.
So that's why we centralize it. Basically, we find the mean and then we do this step. So basically, C is the covariance matrix in this case.
Generally, we call it as a covariance. I will back to the second and third.
So variance also we reduce, right? Because if we have to be close to the mean,
No,
then
so this so that is what I want to tell. The variance is maximized. So that let me complete it. So that part is remain still. So what is happening here? So this is the projection part we did. So we understood that we are anyhow we are projecting it. Now what is happening? Why we want to maximize the variance? So let me tell you what is happening here. So maybe I will make the same picture. Okay. Suppose the okay. So here as we are able to see. Okay. Suppose here we are able to see. Uh, we are projected data and able to see the separately, right? Here is the projection, here is the projection. So let me change the color. Visualize. So suppose here is the we projected and separately we are able to visualize. Okay, here is we are able to visualize. But suppose the case is we are projecting the data on here. Okay, and so many data on the same. Okay, suppose here is another data and we projected here. So this is very close to that. This is very close to that. This is very close to that. So many data we are still projecting, which is very close. So see, after projection, the data are very close. Okay, this is what is happening. The data are very close, very close. Sometimes on it itself, on means another projection on the same, not exactly same, very less. There's very less error. It's beside of that projected
What
data.
close to what? Close to what, sir?
Sorry, close to the second one projected data. Suppose here is one projected data. Suppose, okay, let me erase it. Suppose you projected this data to here, and here is another data. Okay, here is suppose here you projected this data, which is very close to you projected here, right? Which is actually very close to this, the which you have already projected. Second projection means this you have another this data you projected on this line, okay, which is very close to the which you have already projected. Means the projections are very concise here. Projections are very concise. Means they have not, you are not able to distinguish which, suppose you want to distinguish, okay, suppose this is the projection here. You want to distinguish which data is projected here, which data is projected, because so many data are very close to it. Either is this one or this one is projected to here or this one is projected to here. It is very difficult to distinguish which one is projected to here. So here is we are in this sense we are maximizing the variance. In this sense we are maximizing the variance. So data would be somewhat, sparsely we are able to see. We want to project on that principal component. Not only it will reduce the reconstruction error, it will also we are able to also visualize the all the data where it's actually projecting. It should
In
not
respect to
concise.
in respect to what is the thing we are trying to understand, means what is the part of PCA we are talking about here?
So means we are anyone can, we are projecting somewhere on some principal components. We have so many data, we want to find some important component or important direction or principal direction. On that direction we are projecting the data. That is what we are doing in PC. Okay, and not only projecting, once we are projecting so many data, we want to project like that, so that the projection would be not very concise. It will be some sparsely. We are able to visualize, okay, this data is projected here, this data is projected here. We are able to segregate separately. Not it should be very close. Are you all of you are able to understand or not? I don't. This is
Sir,
what is happening actually.
may I ask one doubt? Like
Yes.
in the week 1 or week 2, we had a example use case that in the supervised learning, we discussed about the price of the room, the some like the number of basically house price, right? So how many rooms are there, the distance from the metro station, then the locality, all this, and then we try to predict. with that
Yes.
example, if we want to correlate and understand how we can apply PCA in that use case.
No. So that is PCA. That is not will do PCA. First of all, PCA is does for unsupervised learning.
Okay.
That
Okay.
is
So,
you are doing for supervised learning. This is unsupervised learning.
okay. So where the outcome is not known, it is a not level data, and
Not labeled data.
yeah, and we
Correct.
want to understand what is critical component for us.
Yes. We want to understand which component is. We want to get some direction, proper direction, where once we project, the projection is also different. So we want to project there so that the new data after projecting, these are the projection you have. After projecting, these all the new constructed data you got, and from the original and the projected one, if you subtract, this should be lesser one also, and not only this one also. You projected here, the projection is not so concise. It would be, your the projection you are able to see it, means in the mathematically here it means to say, not it should be very concise. The variance should be maximized also. So PCA is actually, we want to do this like this. We want to do like this. So PC algorithms actually give such, means if you proceed with this algorithm, okay, whatever this one is saying, if you proceed like this, so not only the reconstruction error would be lesser, the maximum also would be, sorry, variance also would be maximized. That's why the PCA is important. This is what it's happening. PCA is one algorithm. The first thing is that we want, suppose these are the data we have, okay, we want to find some important direction where we will project these data, so that it will be no need to work with all this data. Only this working with this data would be enough, means after the projection. Okay, that is what the first thing is. So once we projected it on this important direction, this is called your principal direction, where we are projecting it. So not only after projecting these data, okay, means if you, so the thing is that we want to, after projecting it, not we want to find such that, so that this new data after projecting it, okay, means this error, this error would be lesser. This error would be, means the distance it would be lesser. The first thing is that, and after the projection, the datas are not so concise. It should be sparsely, means various. We want to such that we want to get some variance also, maximize kind of variance. So if you proceed with this algorithm, then both will be satisfied. Not only it will do the minimizing the reconstruction, it also maximize the variance. That's why we used to study this PCA. And what is a PCA? We have data, okay, we will find the covariance matrix, that is generally called, we are trying to centralizing the data, okay. So if you're not able to get, forget about it. So see, so what we does, you have a data, what we will do, we'll find a covariance matrix, which is the formula is here. Okay, once we found the covariance matrix, okay, then we easily can find, so many times we have the eigenvalues, eigenvector. Last time even I think we have seen the eigenvalues, eigenvector so many times. We have, so you SVD also we did. So eigenvalue, eigenvector you will find. So once you find eigenvalue, eigenvector, arrange accordingly, means in decreasing as means the first one is your most, means maximum one, then lesser one means in the decreasing order you will make it, and according to that you will collect your eigenvectors also. Okay, according to that you will collect your eigenvectors. Now the question would be, on means you want to project in 2-dimensional, 3-dimensional, 4-dimensional, as the question is asked, okay, or maybe in the problem statement really said that, okay, project your data in 2 dimensions, project your data in 3 dimensions. So according to that, okay, according to that you can proceed. You will substitute your m values as it is set 2 or 3 or 4, how many dimension it's set to. Project your data according to that you will write, okay, and according to that you will, these are the eigenvector, right, it, these are the eigenvector. So according to that you will proceed with this projection, and the rest remaining eigenvectors, okay, remaining eigenvector will be projected by this mean part, x bar. So separately you will project, and this is how you will get the reconstructed vector. This is your new or reconstructed vector. Means here these are the where you projected your data. Means this is what you got your data, which is your this one. And now
Sir,
this is
this is
means
something. This is something
Let's
like.
go to some example.
I will tell you the example. Now I will give the example. So is it clear what is happening at least? Okay, is it bit clear at least? Okay.
Sir, this is
what it's
advanced
happening.
advanced version of the dimensionality reduction. Is it like?
Yes, you can say even that case. You know, encoder, decoder.
Yeah,
Encoder
encoder.
reduce the dimension. So we used to transform directly data with the T, means using the some transformation, but this is a different transformation. This is a different transformation. It's a kind of projection we are doing.
So basically, this projected vector itself is the reconstructed vector, right?
This projected vector is a reconstructed vector. Correct. Okay. So let's do problem. I have solved this. Okay. So this is what exactly this is done. This is what the PCR. Now, if you want to see it, what is the proof in it? Why it is happening? So everything, because so you want to see it, why it's happening? Why this is giving less error? Why it is giving the maximum variance? So for that you can see the proof why it is so. But
Sir,
the
one more
PCA
doubt,
is,
sir. Yeah, sorry. Sir, is it having any relation with the SVD, single value decomposition? Like
no, there is till now here there is no relation. I think there is no relation with the SVD. The species by certainty. Yes.
There also we broke the actual metrics into the three parts. So I'm just trying to understand a little deeper, like how, if any correlation with whatever we know already. No, right? It is totally.
So the correlation is here happening. First is projection, okay, and also MSC, okay, mean square error, and eigenvalue, eigenvector you studied. That is what it's happening.
Okay.
These are the relations which we studied previously. Yes, there is no relation with SVD, but except that rest all it is related here. Eigenvalues, eigenvector, symmetric matrix, orthogonality, and this real eigenvalues, eigenvector. These all are actually related here. See, this covariance is your symmetric matrix. Okay, so it have real eigenvalues, and this eigenvectors are going to be orthogonal. So many things are actually related, which told in the proof. So you can easily get it. Okay. So many things are actually which you studied previously. Yes.
Sir, I just have one query because actually, yesterday also I raised some queries on discourse related to basically the projected vector and the reconstructed vector. Sorry, I'm coming back to this part again. Just take a minute of yours. The thing is that actually I saw across on the internet actually across many sources, and in a lot of sources I they mentioned the projected vector is not the reconstructed vector. So what they did basically for the projected vector, can you just go back, sir? Can you just show that formula once?
Yeah.
So basically what they are doing, the projected vector they are finding from the first part of the formula, sir. Okay.
This part only. Yes.
This part.
Okay.
Whereas the reconstructed vector, they are finding it by adding the second part. So it is the whole formula basically.
Okay. Got it. Proceed.
So basically, found a lot of topics wherein these things were mentioned. Definitely, I served the LLMs also. I served ChatGPT. I served on Perplexity also. I served on Gemini also. So a lot of those things were giving the same results. And also on the internet also I searched for a lot of information wherein they were giving this result only. So, sir, just if you can have some discussion maybe with your team and all.
Yes. I will. Let's discuss on this one. So, what is happening here? Yeah, you are totally right. So, we are projecting here this one. This is the you are saying this is the projection part.
Yes, this is the data.
And once
set.
we
Yes,
are once we are adding, so this is your reconstructed data now.
Correct, sir.
Okay, this is your reconstructed data now. So that is what I said in starting. Our projection is not exactly this one. We will proceed with the as in the formula.
because
But I
actually,
want to explain this in the projection format. That's why I use the word projection. Otherwise, our projection formula in the PCA is different, as you are saying.
yeah, because even like the professor used this entire formula. So like nowhere he used this word the reconstructed vector. So because whenever we are finding the reconstruction error, so we are worried about the reconstruction vector, right? Because first we have the original data set, and that then we have the reconstructed vector, which we which when we add the mean part to the projected vector, we get the reconstruction vector. So that is a bit of a there is some ambiguity in this thing.
So yeah, so the thing is that the first thing is, I don't think you actually went too deeper here. So I don't think maybe it would ask that the projection one. Actually, always should be asked reconstructed, because professor is not went in so deep. Okay. So yeah, this is the projection part. That's totally fine, and this is your reconstructed vector now.
Okay. Because in
Okay.
some of the PA questions they ask projected vectors basically.
Oh, okay.
That's why, sir. And also, I tried when I did that problem. So it was considering only the first part, basically.
So what is in
Answers
that? The problem is asked for projection or on reconstructed. What
projected
is
vector.
asked there?
Projected vector.
Okay, projected vector.
Anyway, sir, we can come to that later part. First, we can discuss.
Okay.
Let's solve one example.
So yeah, let's discuss with example. Okay, this is how it is. I hope all of you able to at least understand. So I actually with the word projection, because to understand the mostly I focused more on the variance part, because many people have usually doubt where is the variance, why we are maximizing the variance. So this is what the variance. That's why he uses the projection here word. Means we are actually projecting it. Not actually. This is the projection is a different formula, but this is what actually we are doing, and the variance is like this is happening. That's why we are want to maximize the variance. We want to don't concise the vector. We have to some sparsely it should be projected. Okay, let's do one problem, right? So I will directly jump to the solve with this one, because I want to finish the both. So that's the good thing, and also it is solved here. And so the how it would be asked. So let me proceed with one. So first I will give you some. I will try to give some time to you also, because I have done the whatever the theory part I want to tell. I told you. So I will give some time to understand yourself. Try to understand. Okay, and then if you are not able to, we'll proceed with this problem with the solution. So this is what it is here. So these are the data we have. Okay? These are the data we have. This is the data we have. So here separately it asks mean vector, okay, covariance matrix, eigenvalues of it, eigenvector of it, and transform the data. And now the data point on one-dimensional PCA says, okay, this is only one-dimensional, and find the reconstructor here. So here is question would be asked, find the one-dimensional PCA. Which one is your one-dimensional PCA? The question would be asked like that. Maybe I can transform this question to find the one-dimensional. So not only one dimension, find the principal component. Find the principal, okay? Principal component. Which is your principal component? This is what my question. And the reconstruction error is fine. That the projection means the formula. So after substituting in formula, the getting the correct one is your reconstructor, the reconstructed vector. Okay, this
How
is
to
the usual one. This is the final step. But I want to here find the principal component. Which one is your principal component? Where you are projecting. So do this one by one step. Even this is separately wrote. All steps are asked in the question page. So all of you do it, and let me know something. First of all of you do. Maybe if you got some answer, you can put paste in chat also, so that I at least know you have done that, and then we will discuss this also. You will do MLT, everything would be very much clear. Here also a bit clear, but so professor is not discussed with the picture, but most of the thing did in the theory. Okay. Yes. Yes, Kiran. Do you want to say something?
Yes. So when is the solve with the session for this week?
Uh, this is what I am doing. Like almost I have did the theory part. So that is what we are doing the solve with us, because we have to cover the week 8 also. In the next week we have to do the revisions also. So this session will do solve with us and uh, open both, and in the next week, next session, which is on Saturday, we'll do the for week 8.
So what's the question? Question.
So who didn't go through with the lecture, okay? So do not worry. At least if you understood here what we are doing, now if you see the lecture even, that would be more understandable also.
What's the question?
The question is this one. I hope you're able to see my screen.
Yeah, but I didn't understand what you said.
So the question is this, these are the questions means in these steps. What is the mean of the vector, mean vector, okay? Covariance matrix, eigenvalues of covariance matrix. This is what it is given. No? So mean is, just add them and divide by 3. So this is your x1. cos x2 plus x3. You will get a mean vector. This is your mean vector. Covariance matrix is according to that, write your covariance matrix. Now you are able to see it easily. You can, and eigenvalues of it, eigenvector of it. Principal component is what I want to, that is what I want to ask even. That is what I am asking. And the reconstructor is according to proceed with the formula.
So this is one of the eigenvalue 5 by 3.
5 by 3 and
5 by
what
3,
about the,
2 by,
what?
2 by 3 and minus 1 by 3.
Okay. I don't know. I have to check. Proceed with this with eigenvalues. Find the eigenvectors.
Sir, hello. Sir, am I
Yes.
audible?
Yes, you are audible.
Sir, I'm having trouble after the step of finding the eigenvalues and eigenvector. I solved with the matrix. Can we just discuss after that?
Sorry, you stuck with on the eigenvector. Then you stuck how to find the principal component.
No, I am stuck at the third eigenvalue matrix C and eigenvector of matrix C.
Why is it tough? We have done right so many eigenvalues, eigenvector lectures.
Yes,
Are
we
there
have done,
three,
but
four?
still
From 3, 4 we are doing.
I am still not confused with this.
Eigenvalues, eigenvector.
Yes.
Okay. So eigenvalues is if you have a matrix, then just do A minus that matrix A, or here is C, C minus lambda I your identity.
Sir, the matrix after computation I got is 1 upon 3, 2 minus 1 minus 1 minus 1 2.
Okay.
Are we
So once you found the matrix, then you don't know how to find the eigenvalue.
eigenvalue is minus lambda in 3 sides.
Just do that. If you have these are the entries. So if you have this matrix minus lambda, your identity matrix. This is what you will do, right? And find the determinant of it and equate it to 0. And whatever the root you will get, that is your eigenvalue. Easy. Just proceed with this.
Eigenvalues, eigenvector formation is eigenvalues. I got the 3 eigenvalues. I got it.
Okay. Now the next step is once you found the here eigenvalues, so just substitute in this matrix in this portion. Just substitute it lambda values, okay, and solve the whole matrix. Means write the one single matrix, okay. After substituting lambda values, write the single matrix. Means write easily can write because lambda will substitute, multiply it, subtract it. Means whatever the addition or subtraction is here in the matrix case, find that and one single matrix and solve this system of linear equation, homogeneous. Solve this one. You will get infinitely many solutions. Choose one of the vector from that. Means generally not scaled up. We generally choose not scaled up. So
Dependent,
choose that.
independent.
Find that vector. Finding the solution, right?
Yes,
You can
yes,
anytime
yes.
share. So proceed with it and then let me know where you reaches.
Is anybody got the answer?
Anyone wishes to the answer?
I have got only one eigenvector. Working on the other two. Done some calculation mistake actually.
So quiz 2 syllabus is, don't be confused. Week 1 to 8 would be good to understand it. 5, 6, 7, 8 would be there. More emphasis on 5, 6, 7, and 8. Not 6 to 9. Yeah, this is yes. Yeah, week 1 to 8. Yes.
Eigen value is 110.
Okay, let's see it. Can we proceed with the solution?
Yes, sir.
Maybe someone is solving.
Let's go ahead with the
Okay, let's proceed.
Okay, sir.
So what is here? See, this is the data we have: x1, x2, x3. So what we will first find the mean vector. So mean vector, how we'll find? Formula is mean vector is just 1 by 3 of x1 vector plus x2 vector plus x3 vector. Means add coordinate wise. Okay, add coordinate wise and divide by 3 each coordinate. That is what you know generally, because this is a column matrix. So if 1 by 3 is there out, that means you have to divide by 3 each entry. So if you do this, we'll get this column matrix. Means this is the vector we'll get, the mean vector. Vectors are nothing but the column matrix we generally say. Okay. So this is the mean vector we got. Easily you can verify. Okay. If you want to verify, even I can verify at least one first entry. So this will give 3, and this 2 will give plus 3, and this is 6, right? The first entry is going to be 6, but if you divide by 3, then it will be. Similarly, you can count the others also. So this is how you can calculate the mean vector. Once we found the mean vector, then we find the covariance matrix. And covariance matrix is formula. Covariance matrix formula is slightly different, which is here. See it how it is. You have the x1, right? And you have the mean xi. Okay. And again the same matrix, sorry, same vector with the transpose one. X1 minus mean and transpose. And similarly, you will do for thrisely, for 3 times. Means for each vector, x1, x2, and x3. And by this way, so if you thrisely here, which is done here, if you see, this is your x1 minus mean. Okay? And this is your transpose one. Similarly, this is your x2 minus mean. And this is your the same transpose one of it. Okay, and this is the third one. This is your third one, which is your x3 minus mean, and this is your transpose one. And this is how you will do separately. You will get the covariance matrix. This is your covariance matrix. Once we found the covariance matrix, then we have to find the characteristic equation. As you know, you used to find the eigen values, and I told just now how you will find. This is the way to find the eigenvalues, and many times we did also. There are so many weeks we spent on eigenvalues and eigenvectors, so I hope you can do it easily. And also, I just now told the steps also. So if you proceed with, so we'll get the eigenvalues 3, 3, 0. Somebody's got 5. Okay, is this one?
Sir, because so can you just go down?
Okay.
Yeah, characteristic equation is this 1/3. Actually, I got 5/3, 5/3 minus 4/3. How?
Okay.
So because sir, it will become 2/3 minus lambda, right? 2/3 minus lambda, 2/3 minus lambda, 2/3 minus.
Yeah.
lambda.
Yes. Yes.
I think, sir. I don't know how. I'm getting 5/3. 5/3 I'm getting 2 times, and minus 4/3 once.
Sir, even the trace is not sum of eigenvalues.
Oh.
They have to be 1, 1, 0.
Okay, let me verify. In window calculator, let me proceed with the first one. The matrix is generally, I think this is the good one. Yeah, I think this is 2 is there. Anyone can quickly tell the matrix? 2 and then minus 1.
Yeah, minus 1.
And then minus 1.
Minus 1, 2.
This is 2.
Minus 1.
Okay.
Sir, it will.
Minus
Sir,
1, minus 1, 2.
I think each, sorry, here is I will divide by 3. Sorry, here what is here?
So I think I have done a mistake. Probably that is right.
Okay,
Minus
what is
1.
here? And the next is
Minus 1.
minus 1. Okay, all are minus 1 and the rest is 2.
I have done a mistake. Probably that is right, sir. I concentrated on 2/3. I forgot to take minus 1/3.
This is, I think 1/3 each time I have to just do it, right? I missed this. 8, 68.
Got 110.
110. Okay, if we do the diagonal of it, what we'll get here? Let's see. 110001. Right. So there is a mistake. I think he didn't divide by 3, right? This is what should be. Right? This is the mistake, I think, here. And eigenvectors corresponding to that is going to be this one. For 3, 3 means here 1 by eigenvectors are going to be same because there is no impact. If you verify it here, it is going to be the same. So that is what we want to the component vector. So you see the eigenvectors are here only 1, 1, 1. These are the eigenvector, I think. For 1, for 0, it is 1, 1, 1. For 1, it is minus 1, 1. And this is what it is. So let's see it. Yeah, this is what. For 1, eigenvectors are going to be same. Okay, and eigenvalues are maybe slightly here because in here it is not divided by 3. So this is going to be each time by 3. If you write, this is going to be 1. So this is going to be 1 only. 1, 1, 0. Eigenvectors, if you calculate, this is. So many people have generally doubt how I can verify I am doing the correct eigenvalues, eigenvector. You can do this eigenvector calculator. This is a good one. Generally, you can use it. Okay, easily can many things you can find. It's VT means
Can you share
to
the
verify
link?
yourself. I just do the Google search and I got. So
Okay,
just do that. This is matrix call or something is there. I just did the Google and I chooses the second one. I mean, see, this is Yahoo. So easily means to verify yourself. You cannot even, this is not provided in the, in exam. So this is to verify yourself that I am
It should be provided to the exam, sir. This should be provided.
Okay, so this is how you'll calculate the eigenvector, eigenvalue. So here is actually written the proper steps also. So this is that's why I'm not suggesting from my side, okay, but I'm just giving the idea that you can verify each time. Like, see, if you click on the detail, you can see one by one each steps. You can do that, understand. Okay, this is how you can verify yourself. I'm proceeding with the correct answer or not.
It is much better than ChatGPT and all.
Generally, I used to do I used to verify myself by this. So let's do. So this is the eigenvector. So the principle is if you have two different eigenvector corresponding to the same eigenvalue, then use any one of the eigenvector to find one-dimensional PCA, because there is no different or there is no information made in the lecture that if you have the same eigenvalue with the different eigenvector, then which one we choose. So that's why here you can choose any of the eigenvector. So I said no, I want the principal component direction, principal component also. Principal component I want one-dimensional principal PCA. That is called one-dimensional PCA generally. So your one-dimensional PCA is this your eigenvector. This eigenvector is your one-dimensional PCA. This is for both one. It is here. For both it is one. So you can choose any of them. It doesn't matter. Okay, but this is your one-dimensional PCA. Okay, either you can choose this or this. Okay, why it is so? Because we will first arrange in the increasing order. Sorry, in decreasing order. Means it is not 1 and 0. It is. This is how it is. So this is how 1 and 0. And according to, we'll choose the one-dimensional. So corresponding highest eigen means we'll choose the top eigenvalue and a corresponding eigenvector. This is your one-dimensional. If it is two-dimensional PCA, suppose it is asked two-dimensional PCA. So in that case, okay. So in this case, both the direction is going to be the one-dimensional PCA. Okay, so we'll choose just two. So maybe you can choose both two. This is how it is. But if it is three-dimensional PCA, then you will choose the third one also. So how, in which dimensional? One-dimensional, two-dimensional, three-dimensional, four-dimensional PCA is asked. According to that, one by one, you will choose the eigenvector. This is first. Okay. And now the main idea is, see, here is also projection is wrote. So then maybe the reconstructor, okay, transform data. Also, see here it is also clearly. So somebody's asked with the confusion. No, even I
yes,
I was see, this is here the projection data.
Yes, correct, exactly. These are the projected data points, sir.
This is your projected data. Here is also clearly mentioned it. And now the reconstructed or transformed data is added with the
Right.
the mean.
Step 5, you please.
Yeah, I will back to this. Yeah. So step
please,
5 is.
So please do share this notes, sir, on or upload on the.
I will share it. Will give to upload it. So With the step 5 is this is the 5 step 5. So in the step 5 is I am just finding the eigenvector. Confusion? Still confusion? How will find the eigenvector? This is your eigen covariance matrix. I hope everyone able to find it. When this is the formula, this is exactly the formula. Just need to proceed, and also here it clearly done this one by one. I just wrote here separately. Only what is remain here? This is your covariance matrix. Now this matrix minus, I'm removing here, so I'm minus, this is your minus lambda time identity matrix. Okay, lambda time identity matrix and the determinant of it, and determine n equal to 0. Root of it will give your eigenvalues, which is 1, 1, 0. And eigenvectors, eigenvector is now one by one you substitute the eigenvalues here, okay, and solve the expression in the matrix form. Whatever the matrix here, the operations are given in the between the matrices. Solve that and find the single matrix, and now solve this system of linear equation. Okay, this will give you a eigenvector. Okay, you can proceed. Even if you have a doubt, you can. So that's why I'm skipping, because many times we did. So you can proceed with this matrixsquare.org there, and you can many times you just change your you change your entries and try to find yourself, and if you're not able to reach see the solutions, okay, try to do more practice so that you will be comfort with the finding eigenvalues and eigenvectors. See, this is very clearly he did that. He find a minus lambda, a determinant of it, and equated to 0. See, very clearly he did. See, this is what he did, and this is what he found the characteristic equation. This is what equal to 0, and this is what he found the roots, which is eigenvalues. And now see, again he proceeded with the a minus lambda a. V is your xyz. That is what I am saying, xyz. Now see how it's solved. He uses the Gauss elimination method to solve it. See, these are the steps he follow. This is the Gauss elimination method. He will clearly even tell that, okay, how he got this entry, this entry, this entry. Clearly he will tell, and he finally solve using the Gauss elimination and reaches to one solution, which is this is which you will reaches to the solution. This is your eigenvector. Each steps you can clearly mention it here. So do some text from somewhere, from anywhere, okay, try yourself and verify with this. You can verify it.
This type of questions lay down every scores. This type of questions.
Yes. Okay. Yes.
Even the maximum
So
practice
this is
lay down.
yes. Now all of you can do more practice on eigenvalues, eigenvector. Even see, not only that one, not only this one. Change the see. So many things are there. Okay, this is not. These two are not important. Jordan and decomposition. Singular value is there. See, many people have doubt. Okay, how I will do? Just change the matrix, and so means you put the entries different and find the SVT and practice yourself so that you will be very comfort. And here, if you do this, see here it is give the detail to see how he is doing. Okay, very same thing he's doing. See it very clearly he's doing. Okay, so that you can verify yourself and also practice yourself. Okay. I'm not promoting this, sorry for this. I'm just giving for you to do more and more practice to be very comfort in the exam. But that's okay. So eigenvalues, eigenvector. So this fifth step is finding the eigenvalues, eigenvector. And now see the projected formula. So again, I'm writing the formula here. Let me write the formula. The reconstructed before to find the reconstructed. So let me write the reconstructed vector. So reconstructed vector xi tilde, which is your summation I is equal to 1 to m. M is your in which how many dimension means one dimensional projection. Sorry, reconstruction means one dimensional PCA, two dimensional PCA. According to that, your M is going to be, and then this is okay. The original vector. The projection formula is actually exactly the projection formula. X1. Okay. So here is I would be there, Xi. Okay. And transpose and Ui, your eigenvector, and outside Ui. Yeah. Be sure with divide with the norm. Okay. Don't forget, because these are the orthonormal. Sorry, orthogonal. You have to do with divide with the norm. It will be ortho. Normal. Okay.
Yes, sir. In this case, they are exactly following the projection formula.
Here is exactly the projection formula, and now this part is called a projection here. Okay, this is what here is the projection word. Now in the next step, and the projection with the mean. Sorry, this is I is equal to m plus 1 to d. Okay, and this is mean. This is mean. Mean is going to be there. So mean, and this is transpose. I forgot. No? This is here the transpose. This is xi transpose 1. So mean transpose, and then ui, and outside ui. So this is what it is. See it here exactly. The reconstructed vector is this one. This is exactly. See here is the elaborated, means I just wrote in the summation form. This is what it is. Here is 1. Here is 1. So u1. So x here is this is for I format. No? This is for I format it wrote. Okay. And so x1 is going to be, according to here, let me write here is x1 is x1 transpose u1 outside u1 plus mean transpose u2 outside u2 plus again mean transpose, okay, mean transpose u3 outside u3. These are the projection form. These are the exactly projections. Separately you are doing the projection. These are the projections formula. So see, x for this x1 you did. Similarly for x2 you will do, x3 you will do, and x. So yeah, 3 vectors are there. So separately you will do. So here is everything is did here. Okay, you can first find the. So try to find here is did the project. So this 6th step. This portion is done. Okay, this portion is not done here. Okay, only this portion is done. So x1 u1. Okay, because one dimensionally 1, so here is m is going to be 1. Okay. So only 1 is nothing. No need to write here the summation. Only just replace with the 1 So x1 u1. Okay, once you found that, then outside u1. Okay, is not multiplied. Should be multiplied u1.
Sir, I think it's multiplied in the next step, probably.
Okay. Okay, maybe.
Might be. Yeah, it should, in general, it should, yeah, they are not multiplied.
Not multiplied. So actually here should be multiplied. Actually, what is here? Projection of u1, x1 on u1, he just wrote the, I don't know why it is wrote, how it is. It should be the vector.
Sir, actually, they have just calculated the scalar part. Then probably after that, they will be multiplying with the vector.
Multiply with the vector, which is your eigenvector, which is here -1.
1 0 1
u1 is -1, 1 0. And here is again, here is x2.
Only week 7, only PCA is there.
Yeah, week 7 is totally PC.
Sir, into 1 by root 2 is also there, sir.
Into yeah, 1 by root 2 will be there. So that is why it is going to be 2.
Yes.
Okay. So here is not going to be I. Here is not I, because it will be how many dimension we want. No, so this is xi uj. Check the formula. uj. I mean, actually, just let me write the formula in expanded form. Here it's already wrote. This is the formula. Let me write here x1 separate. X1 tilde is equal to, okay, x1 transpose, okay, u1 and u1, okay, plus with the mean here, x mean transpose u2, okay, here is u2 plus x mean transpose, yeah, mean is there, and u3 and u3. This is for x1 tilde. X2 tilde is going to be, okay, for x2 transpose u1 outside u1 plus x mean transpose u2 outside u2 plus x mean transpose u3 outside 3. Now x3 tilde is going to be x3 transpose here only u1, okay, and x mean u2 transpose, x mean u2, x mean transpose, and here is plus x mean transpose u3. Now just need to substitute the values here in the exactly on. So you can, x1 is from the given data, okay, x1 is will get from the given data, u1 is your here, u1 is your here already, u1, u2, u3, okay, and mean is already you have calculated here, the mean one, this one, this is the mean. So everything is there, only just need to substitute, multiply, and one by one need to get this one. That's all. Means just solve this all. Just need to substitute, multiply, and solve. That's all. Means sorry, calculate the vector. One by one. Here it is calculated as in the here. This is what it is calculated. x1 tilde, x2 tilde, x1 tilde is this one.
Reconstructed vectors.
So this is your finally reconstructed vector. Now sometimes it asked find the reconstruction error. Sometimes question would be asked find the reconstruction error. So how will get that? So simply because this is your now reconstructed vector. So from the original one x1, this is your original, it's given, and the reconstructed one, subtract them, find the norm of it, square them. Okay, this is the first one. Similarly for the second one, second reconstructed, find the norm it, square them. And now next is for the third one, original one minus constructed one, distance, norm is generally, all of you know, norm is generally to find the distances. Okay, so and add them, this is your going to be the reconstruction error. Variance is what? Maximum variance is maximum eigenvalue. So in this case, maximum eigenvalue is, here is wrongness, 1 is actually, so maximum variance is the maximum eigenvalue, which is 1. We see, is this step is clear? Yes, proceed. You can.
Sir, there were two eigenvectors for lambda equal to 1, right? Which one should we take as u1 and u2? Like, is it our choice?
It's your choice. It's totally
Okay.
on your choice, because here is a note, in the note it's written. Maybe then in that case, answer may be different, but this is how it is. That's all. If you
So in case, then we will probably have to check the reconstruction error in that case, right?
Yes, that would be good. Maybe in this case, error would be, I don't know. I have to check one. But yeah, in that case, best is to find the reconstruction error. Which one is going less error?
So in first step, how you are calculating the mean? Like
mean is
vector wise or in a matrix?
Coordinate wise, you just no. Coordinate wise, you have to add it. The first coordinate added with each time. This all three will be added and divided by the number of data. This okay? This is the number of data. Coordinate wise, you have to add them. That's all.
If we make matrix of all three, then it is like
No. So if you do from your side, then now this is you are not following the PC algorithm.
no. If we make matrix of all three vectors like x1, x2, x3, make a matrix, then find the mean row wise like you are.
So if you are making the matrix and then finding the mean and then you are adding the row wise, and in the last, so that is you can do for yourself, but that is not you cannot write if somebody is asked find the in the handwritten way, so that is wrong, no? Then what is the mean of it? You are writing in the matrix form and then you are pulling out from a vector from there. What is the mean of it? That is not the correct way to write the matrix.
After finding the mean, we have minus from the vectors on a x1 vector. Like
yes, from the original one and the mean. From original and subtract from the original, subtract the mean. From the original, subtract the mean. Here is from x2, subtract the mean.
Here is confusion because in both sides we get only 3. No? Same.
Both sides? Both sides will get 3.
No,
so both sides you will
mean
get 3. Both sides you will get.
Mean is 2 from both sides when we take column wise or row wise.
Mean is 2. No, so only we'll go with this one. The best thing is just go with this formula, because this tray tells by the PC algorithm. Yes, this is your PC algorithm. Don't go with the row wise sum.
Here x1, x2 are what? In this formula.
Given data.
No, given data I know, but 1, 2, 3 is x1, x2, x3, or it is a vector, full vector.
No, the full vector. This is your full vector. Full vector.
Okay.
Okay, can we do the next problem also? Let's do with the two-dimensional.
Sir, just a small doubt, sir. I need to confirm. Sir, if it asks for two-dimensional, then for the projection of data points, we need to multiply by the second vector, no?
Suppose your formula, suppose it is asked for two-dimensional. Suppose it is asked for two-dimensional. This, in that case, what is going to be? So in this case, the formula is going to be slightly changed. So see how it is. So x1 tilde is going to be x1, okay, x1 transpose u1, okay, and then outside u1 plus, okay, and then x1 and u2, x1 transpose u2 outside u2, and the last one is only the mean one. The last one is only the mean transpose u3 and outside u3. See the differences here. See here is your mean, and at the second term here is your mean, but here is your not mean. It is the vector, original vector transpose. So this is the difference between two-dimensional reconstruction and one-dimensional reconstruction.
Sir, irrespective of the lambda value, like say for example lambda for u1 is higher.
So this is already this u1 u2 is according to the higher one.
Okay. But in case of two-dimensional, we'll have to do like this, right?
And two-dimensional, like which one?
x1 transpose u1 plus x1 transpose u2 into u2 plus mean of x transpose.
Yes, this is how. Because how many means in which dimension it says according to the mean one is going to be the removing part, means on which dimension, means two-dimensional saying according to that till that 2 will go. Means you follow the formula. I just wrote the formula. See, I wrote the formula only. See, better is if you go with this formula. See, how it is, how many dimension is that? According to that, if you just expand that, if you remember this formula, I just expand many times. If you expand, you will easily get that. That is what I
Okay,
wrote
J,
there.
okay, J is for dimension, correct.
Yeah. This J is, see, here is I and J both is given.
Okay, one
That is
J.
what I wrote there. That is what I expanded here for 3 cases. And the difference is what I am saying. And for that one dimensional, see, only here is the same. For one dimensional, here is the same. These two are same, but these two are different. See it here, this one and this one. This one, these two are different. Here is the mean came, but here is the vector came. This is for 2 dimensional, and this is for 1 dimensional. And I am writing this all only from the formula. That's all. That's all.
Okay, say for example, we have the eigenvectors. Like, I'm just saying, just an example. So, we have like 1 by root over 2, 1 by root over 3, 1, 1, 1 plus, then again 1 by root 3 minus 1, 1, 1, and then 1 by root 3 maybe 1 by root 7, something like that. So in that case, we will have to go for this one basically. That's one transfer. Okay.
Yeah, only just need to here replace with this one. No? Only replace this here to.
Got it.
From mean to vector. So if anyone have still doubt, okay, I will tell to TA to do practice problem on it. That would be really good. Okay.
Sir, I had one doubt. Like the question you asked, like what is the PCA? What was the final thing we were finding? Is lambda on the PCA?
So no, so the final thing are so many questions in the PCA. So maybe it could be ask the principal component. One means find the one dimensional PE, means find the one dimensional PE. Means maybe it could be asked the reconstructed vector, means maybe it could be asked the vectors only. Okay, this one, or maybe reconstruction error, or maybe find the one dimensional PCA. Okay, one dimensional PCA. Means find that at highest eigenvector, means eigenvector which have the highest eigenvalue. That is your one dimensional PCA. The 2-dimensional PCA means the first one and the second one. Your 2-dimensional PCA is that. That is what. So it's depend on the question. There are so many types of question. Maybe reconstruction means this could be asked, error could be asked, variance could be asked, or maybe the exactly the component, principal component, 1-dimensional, 2-dimensional. So 4 type of question maybe from here, from in the numeric form could be asked.
So sir, for 2-dimensional formula you have written, so the first 2 terms are the projection data points like we have calculated in step
yes.
6.
Exactly, these 2 are the projection, and this is for the reconstruction, the mean projection. Correct. Okay, so this problem is only just need to do because exactly same with the different number. So almost reaches to this time is 9:56. Okay, all of you do it very quickly. We can discuss. Try to. This is a 2 coordinates in 2D. It is 4 data points are there, and also here is again 1-dimensional PC.
So sir, like we will be given, like, just asking in exam, like we'll be given like transform data points for 1-dimensional PC, or we'll have to find that out.
And the 2-dimensional would be very less chance. Generally, 1-dimensional would be asked because 2-dimensional may be more calculated.
Take time. Yes.
It will take time. and try to, my suggestion is try to understand a bit the theory part also. Sometimes question will be asked from theory also. So whatever we have discussed, I actually try to convince you that what is happening in that in PCA, what is happening in PCA, and now see in the theory part maybe once or twicely. So get that at least so that no confusion would be. Okay, no confusion. Yeah, there is one I missed that high in higher dimension PCA. Okay, there is one lecture higher dimension PCA. In that it said that either you are finding the covariance matrix is A transpose A, okay, or A transpose, okay, but choose the non-zero eigenvalues. Choose the non-zero eigenvalues, and the whatever you are doing means you are doing for A transpose or A transpose A. So if you see the in the higher dimension PCA, sir is not doing any algebra. He is just telling that in place of doing A transpose A, you can proceed with A transpose to reduce the means to reduce the dimension of the matrix. Means in place of playing D cross T, you can play on N cross L for the lesser one. So you can watch that. That is maybe sometimes crucial to understand that, okay, in place of buying this, you can do with this one. Sometimes questions would be asked on that also. So try to understand that also. That is, there is no algebra, only to understand what is going to be happening in the higher dimension space. So I stopped my mic here, but I want to again, anyone have a still doubt related to the PCA, who is doing the problem, let's do that. That's doing, can do, continue. But still anyone have doubt and not able to understand what is happening in the PCA, can ask. No, don't hesitate. I will repeat it again. I stop sharing for a while. All of you have recorded it, so you can proceed. I am just For the timing, I will stop to share you the slides.
So is the reconstruction error 1?
Yes. This reconstruction error is 1. Okay, so I'm giving you the link of the slide to get the link. So all of you easily get it, at least who is attending the session. I'm posting in the chat here. And I will also update calendar. And also it will be shared to via notification.
So it will be shared on the calendar also, or
Yeah, in calendar also have you. Okay, so these are the only in this so I'm just quickly proceeding with exactly the same steps, same just steps are there. Means these are the data you have, data set, and now x1, x2, x3 is there. Yes, you have to just calculate the mean, which is again 2, 2. Covariance matrix you have to calculate, which is this one. Now we have to find the root of it, which is 3 and 1. You can verify it. And now a corresponding eigenvector of it, which is this one and this one. Now this is 3 and this is 1. So 3 is greater than 1. So this is the corresponding eigenvector, which is 1 upon root 2, 1, 1, is actually your one-dimensional PCA. Okay, this is your principal component. Okay, this is one-dimensional PCA. Okay, once you find it, so now this is the projection part. Means your reconstruction part is separately did for the projection part, and for the mean part you have seen many times to discuss, or you can we have this formula. See it. This is your projection part, and this is your mean part. Because mean is there, we are projecting on the mean part. Means projection means both are actually projection. Projection on the data would be projection is both are the projection we are doing, but I'm saying at the mean best is to say projection on data and projection on mean. And this is what the exactly formula is. We proceed with that to find the reconstructed vector x1. So maybe let me raise slightly, make it less. X1 tilde, x2 tilde, x3 tilde, x4, the updated means approximated or reconstructed. So many words usually we use it. So reconstructed vector we got. Now the reconstructed error is again the original one and the reconstructed one, subtract them, find the norm, square them, and sum them, or you give the reconstruction error. maximum variance is going to be the highest eigenvalue. Okay. So I have shared the slides. Go through it and let me know if you have still doubt. Okay. Is it fine? Okay. So I'm stopping now the session. Okay, I hope I tried to convince you this PCA so that all of you are able to understand it. Okay, thanks everyone. Thanks for joining. Anyone have doubt? Somebody's raised hand. Let me know. Want to say something?
No, sir. Actually, just cleared all the things.
Yeah, thanks everyone. Thank you so much.
Thank you, sir. Thank you.
Thank you, sir.
Thank you.